Alrighty guys, we're going to go ahead and get started with these energy notes. So first thing I want to talk about is that with energy, nothing can happen without energy. And this is the truth, right? If you're feeling tired late at night or you just don't have any energy, you're like, ugh, I can't do anything. I don't want to do my homework. I can't get up. I can't take out the garbage, right? Because you don't have any energy to make it happen, all right? Energy is known as the ability to do work, and energy is measured in joules. We're going to abbreviate joules with a capital letter J. There's four main types of energy that we care about in this class. The first is kinetic, then we have potential, elastic, and thermal. We'll talk about all four of those a little bit more in depth on the next few slides. Total energy is conserved, meaning that it always stays the same. Another way to think about this is whatever energy we start with is going to be the same energy that we end with. So let's talk about kinetic energy here. And kinetic energy is just the energy in motion. So in other words, if you are moving, you have kinetic energy. And our equation for kinetic energy is Ke equals 1/2 times m, which stands for mass, times v squared. And v is velocity. So if we look at this, kinetic energy is 0 joules when velocity is 0 meters per second. And like we just said, you have to be moving to have kinetic energy. Mass can never be 0, so the only way to have 0 kinetic energy is to have 0 velocity. If you double your mass though, you will double your kinetic energy. If you double your velocity, you will quadruple your kinetic energy. And that's because velocity is squared there, so you got to remember that. Next one I want to talk about is gravitational potential energy. GPE is how we abbreviate it. And gravitational potential energy is the energy that is stored based on an object's position. So GPE is just one of the many types of potential energy. There's a few of them, and we'll talk about another one later on. But if we wanted to figure out how to calculate GPE, well, that would be m times g times h, where m is mass, g is gravity, and gravity on Earth is 9.8, and then h stands for height in meters. So if you're looking at this equation, GPE is only 0 when the object is at its lowest point, or the bottom, or in other words, the ground, meaning that the object has no height. So the higher you lift an object into the air, the more gravitational potential energy it will have. Next, we have thermal energy, and thermal energy is also known as heat. It's not really useful for getting stuff done, and sometimes we refer to it as energy that is lost. It's always 0 joules at the start of the problem because we haven't lost anything before we started. And usually thermal energy is the result of friction or air resistance. Next, I want to talk about energy conservation. And like we said before, energy is always conserved. If you start with 100 joules, you will end with 100 joules. You cannot create or destroy energy. You can only transfer it. And energy that is lost from potential is going to be transferred to kinetic or thermal for, say, a roller coaster. Over here, I have a simulation of a roller coaster, and you can see as this guy makes his way through the loop-de-loops that his kinetic energy is being transferred over into potential and back to kinetic. We also notice the total energy box right here. It's this yellow one, and it remains at 100 the entire time because we cannot create or destroy energy. So before we start diving into some problems, I would just want to talk about how to set up your problems. First, I recommend you identify the start and end of the problem and draw energy bins. Next, I recommend that you determine which bins are full and empty, meaning which bins have energy and don't have energy. Number 3, find the total energy at one point in the problem. So let's say that you start at the starting point. If that doesn't work, then just try starting at the end. you will have enough information to figure out either the beginning or the end. Then you want to apply conservation of energy to solve for the remaining bins. Solve for all the unknown variables as well at the end, and then you're done with your problem. Alrighty guys, we're going to go ahead and solve this problem right here. So it says a 50 kilogram kid drops to the ground from a branch 3 meters above the ground. So here they are, right? And there is a height of 3 meters from the top of this branch to the ground down here. And we know that their mass is 50 kilograms. We know the height is 3 meters. And this is on Earth, so we can see that gravity is 9.8. So first thing we want to do is draw our energy bins. So at the start, I'm going to go ahead and draw the 3 main bins right now. One of those is GPE. The other one is KE. And then there is a thermal energy bin that's going to be a main one as well. I'm going to write therm here. And then at the bottom, I'm going to do the same thing. I'm going to write my GPE bin. Then I'm going to write my KE bin down here. And then again, my thermal. And you can also add a total energy bin over here so that we can see how total energy is in the beginning and how total energy is at the end. I apologize that these bins aren't straight, but I'm doing the best I can. So let's think about this problem now. At the beginning, this child is at rest and they're 3 meters off the ground. So that means that all of our energy is going to be in GPE. There's no thermal energy because we're at the beginning. And we also can say, just because this is one of our beginning problems, that we are going to ignore air resistance. And I would look in the problem to make sure that it says this, but I'm going to go ahead and tell you for our example problem here. So that means that I have a bunch of GPE, no KE, and no thermal. At the end though, when they land on the ground, their height is now 0 because they're at the ground. So there's no more GPE. So that means all of this GPE is going to be transferred into what type of energy? Well, there's no air resistance. So that means that all the GPE is getting transferred into kinetic energy. And the reason being is right before they hit the ground, this person is moving. So all of that potential energy turned into energy of motion as they fell, and they got faster and faster, meaning that they got more and more kinetic. Our total is still the same that it was in the beginning, because we know that total energy does not change. Now that we have this part of our problem, we can go ahead and solve for it with numbers. So in the beginning, we said all they had was GPE, and we know that GPE is equal to mass times gravity times height. The mass of our child is 50 kilograms. The gravity, because they're on Earth, is 9.8, and the height is 3 meters above the ground. To solve for GPE, we're just going to multiply all those together. We find out that GPE is equal to 50 times 9.8 times 3. And when we do all that and plug it into our calculator, we end up with a value of 1,470 joules. Because we have to remember joules is the unit of energy. Now that we have that, we can go ahead and look at what we said before. All of that energy is transferred into kinetic. So if we have 1,470 joules of GPE, that means that we're going to have 1,470 joules of KE. And again, the reason I knew that was because my height at the bottom of my problem was 0. I'm ignoring air resistance, so my energy had nowhere else to go except into kinetic in this problem. Let's say though that I wanted to figure out how fast this child hits the ground. Well, in order to do that, I would have to use my kinetic energy equation. And that's KE equals 1/2 mv squared. My KE is 1,470. 1/2 is 1/2. The mass is still the same, it's 50 kilograms, and V is unknown. I can go ahead and manipulate this. I get 1,470 divided by 25. I got 25 because 1/2 times 50 is 25, and that equals V squared. Square root both sides to solve for V, and you find out that the child should hit the ground with a velocity of 7.67 meters per second. All right, now that we've looked at this problem, I just want to look at a general case really quick. Let's say that instead of having a mass of 50 kilograms, the child had a mass of 100 kilograms. How would that change the velocity that they hit the ground? Well, some of you might know the answer to this, But if we look at it really fast, we're going to notice that GPE, right, is equal to mass times gravity times height. And we said that all of this GPE transfers into KE, and KE is equal to 1/2 mv squared. So what does that mean? Well, we could just set those equal to each other. So we find out that mgh is equal to 1/2 mv squared. And this is only the case if we are ignoring air resistance. And you're going to notice that we have a mass on both sides. So that's just going to tell us that mass cancels out. So I find out that gravity times height is going to give me 1/2 v squared. This just tells me, again, that no matter what mass the child is, as long as they're both falling from the same height, they'll both hit the ground with the same velocity.